some of the results related to nanosoldering with two different metals that we have had experiments with hafnium diboride and palladium. And then I'll end my presentation with a conclusion. So why do you want to study carbon nanotubes at all? As you can see in the figure on the right, with the animation representing the animation of changes representing the Moore's law, the critical dimension of a device in integrated circuit has been scaled down by a factor of approximately 2 once every year and a half or 2 years. Now, this scaling down has been really the driving force in the technological advance, and it has benefited everyone's life since the late 1970s. However, as the critical dimension has shrunk down to such a small scale, there arise many problems related to device performance, and there are also many fabrication issues. So it has been predicted that a different material needs to replace silicon as the active channel material in future devices. And advanced carbon materials such as graphene and carbon nanotubes are strong candidates that may replace silicon in the future. So what's so special about graphene and carbon nanotubes? As you all may know, graphene is a single layer of carbon atoms that are sp2 bonded in a honeycomb lattice. And carbon nanotubes can be thought of this graphene sheet that's rolled up to form a hollow cylinder. And as you can see in the dispersion relation of graphene, at the 6 corners of this graphene's honeycomb lattice, which are also called the direct points, the conduction and valence bands touch each other with a zero gap, with a linear relationship. And as a result of this unique crystal structure and strong carbon-to-carbon bonding of graphene, graphene has very great electrical and thermal properties. And likewise, carbon nanotubes, which are basically rolled up cylinder of graphene, also has exceptional electrical and thermal properties. For example, electrical mobilities of carbon nanotube-based devices in many literatures are reported to have values greater than 10 to the 4 centimeters square per volt second, with the highest number exceeding that of 100,000 centimeters square per volt second. The electric conductivity of carbon nanotube is also very high. It's about 100 times that of copper. Thermal conductivity is also high. It's comparable to that of diamond. It's about 5 times of thermal conductivity of copper. Now, depending on how this graphene sheet is rolled to form a carbon nanotubes can be either metallic or semiconducting. So semiconducting carbon nanotubes can be used for transistor applications, and metallic tubes can be used for interconnects and such. And because of the miniaturized scale of carbon nanotubes with diameters ranging from 1 to 3 nanometers in general, many different scattering mechanisms are suppressed, so that quasi-ballistic transport has been also observed in CNT-based devices. Now, with all these great properties of graphene and carbon nanotubes, there are also many challenges and limitations related to practical realization of CNT-based devices. Some of those challenges include separation of semiconducting and metallic carbon nanotubes, because as-grown carbon nanotubes are composed of 2/3 of semiconducting and 1/3 metallic carbon nanotubes. Reproducible growth of carbon nanotubes with controlled lengths and diameter and chirality is also challenging. And also aligning carbon nanotubes in a preferred direction and positioning them at exact location is also can be also very difficult. Now, there have been many methods, such as density gradient centrifugation method, to separate carbon nanotubes by exploiting their chemical reactivity based on their diameters to separate semiconducting and metallic carbon nanotubes. And also, there have been many researches to align carbon nanotubes during and after the growth. For example, this work tried to align carbon nanotubes after the growth using a method called dielectrophoresis, where they apply electric field between the electrodes and align carbon nanotubes suspended in solution. And these two methods actually try to align carbon nanotubes during the growth. For example, this work exploited the fact that carbon nanotubes tend to grow more preferentially along the step edges on a surface of a specific substrate, such as quartz substrate. And also, this work applied electric field during the growth between the two electrodes, and so as to guide carbon nanotubes during the growth and align them. Now, these methods can be actually rather complicated, and they also require more fabrication steps, and they also tend to damage carbon nanotubes during the process. On the other end, using the carbon nanotube networks as grown and randomly aligned carbon nanotube network is very easy to fabricate, and it also in itself is also very interesting to study in applications for integrated circuits and display drivers, especially on flexible and transparent substrates. For example, this plot shows mobility versus on-off ratio of thin film transistors based on carbon nanotubes. So these red stars and blue triangles represent thin film transistors based on carbon nanotube networks. And as you can see, the performance of these devices can exceed those of other materials such as amorphous silicon and organic materials. However, one of the main challenges related to these carbon nanotube network devices is that the junction with thermal resistance and electrical resistance at these carbon nanotube to intertube junctions is very high. There have been many theoretical and experimental papers related to this high junction resistance at the carbon nanotube junctions. For example, this work studied a conductive AFM on carbon nanotube networks, and what they found out was that the resistance along the carbon nanotube network has a high step jump at a spot corresponding to this junction formed by individual tubes, indicating the junction resistance is very high. And this work was actually done by one of our collaborators, by David Estrada from Professor Pop's group. And what they did was they actually imaged temperature profile of a carbon nanotube network channel during the device operation. And what they found out was that the average temperature of the channel stayed well below 200 degrees Celsius, but they still observed breakdown of the carbon nanotube networks in their device. So this indicates that the temperature increase at the intertube junction is much higher. So in our project, we're actually trying to take advantage of this high junction resistance in order to improve the device performance. So by intentionally flowing current through the electrodes, through this drain source electrodes, thereby flowing current through the carbon nanotube network, we are trying to locally hit the carbon nanotube junctions. And now we like to do this with the presence of metal precursors in vacuum environment. Thereby, we are trying to deposit metals, nano particles of these metals using local chemical vapor deposition to nanosolder these junctions to improve the junction resistance. Next, I'll talk about the methodology that we use. For our study, we have used carbon nanotube devices with two different geometries. The first one is randomly aligned as grown carbon nanotube networks. And we grow this by CVD using ferritin catalyst. So first, by annealing this catalyst at 900 degrees Celsius, and then we introduce methane and hydrogen gas at 900 degrees Celsius and grow carbon nanotubes for 15 minutes. And using standard photolithography and e-beam evaporation, we define the channel and put down the contact palladium electrodes as drain and source. Another geometry device that we use is crossbar carbon nanotube devices. And for this, we are working with Su Xie from Professor Rogers' group in Material Science and Engineering Department. So what we do is we grow aligned carbon nanotubes on quartz substrate, and then coat gold and PI layers on top of the aligned carbon nanotubes grown on quartz substrate. And using electrometric stamp, we transfer these layers along with the carbon nanotubes onto a target substrate, silicon oxide and silicon in this case. And then after removing the stamp and the gold and PI layers, and repeating this step with the perpendicular direction of the aligned carbon nanotubes, we achieve this crossbar configuration of carbon nanotubes. And then again, we put down palladium as the contact electrodes. Once these devices are all fabricated, we wire bond individual devices, electrodes, to a metal chip carrier. And then we load our sample to our home-built vacuum system. Here's a schematic diagram of our CVD chamber vacuum system. So we have electrical feed-through, so we can bias our sample externally. And we have a nozzle configuration to deliver metal precursors into directly to our sample. And then we pump down our system to a high vacuum pressure lower than 1 × 10⁻⁷ torr. And then we perform a vacuum thermal annealing in order to remove the oxygen molecules that are absorbed around the carbon nanotubes in air. And once that's done, now we introduce the metal precursor into our chamber. Now and then we flow current through our devices in order to hit the junctions and deposit metal to nanosolder these carbon nanotube junctions. We have used two different metal precursors, hafnium tetrahydroborate and palladium LOCP, to deposit metallic hafnium diboride and palladium. I'll show you some of the results now. The images on the left shows the SEM images of carbon nanotube networks before hafnium diboride deposition, and on the right shows after hafnium diboride deposition. As you can see, these small islands of hafnium diboride were deposited at local spots corresponding to the carbon nanotube junctions with high thermal resistance. We also observed some coatings of hafnium diboride along some of the carbon nanotubes corresponding to the most resistive pathways with most resistive junctions. In order to verify that what we are depositing is actually hafnium diboride, we performed EDS, energy dispersive X-ray spectroscopy. The red curve was obtained from one of these bright spots, and the blue curve was obtained with the same conditions on the same device away from these bright spots but on carbon nanotubes. So basically this shows that obtained hafnium diboride peaks are not simply from the physisorbed hafnium diboride precursor onto the carbon nanotubes. We also performed XPS onto this device, and the high resolution inset shows the hafnium diboride peaks, verifying the presence of hafnium diboride. On this slide, I'm showing you another device before and after hafnium diboride deposition. As you can see, in the yellow circles, hafnium diboride were deposited at local spots at the most resistive CNT junctions. And on the right, I'm showing the transfer characteristics of this device in linear and log scale before and after hafnium diboride deposition. The off current basically stayed about the same, but on current increased about 20%. So the total on-off ratio increased about 20%. Now this improvement is smaller. It's smaller than what we were expecting. Many literatures reported the junction resistance at least an order of magnitude higher than those of individual carbon nanotubes. And what we think is actually going on here is because the reason for that is because the work function difference in the work function of the metal that's used for electrodes and the metal that we're actually depositing actually matters. So we are using palladium as the drained and source contact electrodes, and we are depositing hafnium diboride. Now, palladium is high work function metal of 5.2 eV. So when a semiconducting carbon nanotube is in contact with this high work function metal, there's a charge transfer from the carbon nanotubes to the palladium, inducing this p-type behavior at these junctions. However, we are depositing hafnium diboride, which is low work function metal of 3.5 eV, in between these pathways, so that when this hafnium diboride is in contact with a semiconducting carbon nanotubes, now the charge transfer occurs from the hafnium diboride to carbon nanotubes, inducing this n-type behavior. So even though we are depositing these metals at these junctions, thereby increasing the area for the charge carriers to flow and the heat flow, we are basically creating these back-to-back PNP junctions. So this might be the reason that we're not seeing the large improvement that we're expecting to see. Instead, what if we are depositing palladium as the metal to nanosolder these junctions? Then we will have a p-type junctions throughout these entire pathways. So next, we tried a precursor that would deposit palladium, and also we use this crossbar CNT devices where there are fewer number of junctions, and the junctions are well defined. Now, for this device, we use these two electrodes to flow the currents through. And the transfer characteristics in linear and log scales before and after palladium deposition shows a large improvement. The on-off ratio was improved by more than 15 times. However, unlike the nanosoldering with hafnium diboride, where we saw large islands of these metals at the junctions, we did not see those large islands. But we could only see these maybe slight changes in the contrast along some of the tubes near the junctions. And the reason for that, we think, is because the one-function matching of the palladium and the depositing metal, which is palladium and the contact electrodes, when these junctions are soldered, these junctions don't get as hot as the case with hafnium diboride. And palladium is also known to wet carbon nanotubes. Is one of the metals that wet the carbon nanotubes very well. So that may play a role here as well. So in order to test that we can actually deposit palladium onto the carbon nanotubes, we performed a control experiment way where we intentionally flew really high current between these two electrodes on a different device, and in order to over-deposit palladium. And as you can see, the palladium was basically coated along in the entire pathways along the carbon nanotubes. And we performed the EDS onto this device again. So on spot 1 shows palladium peaks, on spot 2 the same device away from this palladium deposition shows no palladium. So again, this shows that acquired palladium peaks is not simply from absorbed palladium precursor on the device. So with that, I'd like to make some conclusions. So we have performed nanoscale deposition of metals at carbon nanotube intertube junctions using local chemical vapor deposition. And we found that the work function of the nanosoldering metal actually matters. And using the right metal, such as palladium, the on-off ratio was improved by more than an order of magnitude. And with controlled conditions, we believe that the process can be self-limiting, and also it can be applied to various types of devices on different substrates. So with that, I'd like to thank my advisor, Professor Joseph Lighting, and our collaborators, Professor Barry Popp and his student Dave Estrada, for the help with fabricating the CNT devices, and Professor John Rogers and his student Sue Xie for making crossbar array devices, and Professor Jerome and his student Noel Chang in the chemistry department for preparing the metal gas precursors. So thank you for your attention.
The talk's now open for questions and discussion. Questions?
Yeah.
I noticed on the second on-off ratio that you showed, the
Yeah.
crossbar. Maybe you explained it, but why is it that your off-state current improved after this thing?
So if you look at the, I didn't really explain that, but if you look at the band diagrams here, so carbon nanotube devices made up with palladium electrodes, in air are p-type usually because the higher function of palladium, so there's a Schottky barrier for the electrons. When you make devices, such as when you make devices, if you just look at the left side here. But if you're depositing palladium at these carbon nanotube junctions, you're creating additional Schottky barriers for electrons to flow between these entire pathways. So we think that may be decreasing the off currents even more.
So before you put the palladium on there, though,
right.
wasn't there just a really high resistance? Well, I guess you went from a high resistance junction to a Schottky junction, and that's either further increase your resistance?
Well, you'll have a, so let's say you did not have this palladium before, then you'll have a certain, off current, current conduction by electrons, right, between drain and source, say. However, you're depositing palladium here, you're creating this extra Schottky barriers here, which, extra barrier for electrons to flow in the off state. So that may be the,
Okay, so
I don't know.
I think what I'm missing is that before you put the palladium on there, those two things were, the two tubes were connected together, right? Which is what created the leakage current. And you're isolating it?
Right, that junction, yeah. So you're still, I guess, by depositing palladium, you're helping, you're increasing the area for carriers to flow. But then in the off state, you're creating another Schottky barrier for electrons. But in the on state, you're actually helping by depositing metals here. So your on current increases and your off current decreases. Did that? I don't know. Yeah.
Further questions?
These dimensions are kind of small. Do you see any like quantum dot behavior in these functions?
No, I have not any seen any quantum dot behavior. No.
There's no like maybe the noise is higher or something. I guess not. Do you know what the dimensions are for the say when you deposit palladium on top of the where these nanotubes cross?
Dimensions of the deposited metal? Well, yeah, so I think I have in the supplementary slide another device where we actually had we have AFM measurements. I don't know if but yeah, these particles are sub 10 nanometers in size. But this actually it really depends on how much current you applied and how long you apply the currents. Because if you apply too high current, then the temperature is going to be much higher and you have more deposition. And it really depends on the conditions they use to nanosolder these junctions, how big particles you deposit. Yeah.
Other questions?
Yeah.
Do you know if the hafnium diboride oxidizes?
Yeah, it does.
It does oxidize?
Yeah.
Okay. So were your measurements done in air or in vacuum? I forget.
The measurements of like the transfer, because they're all done in air.
Oh, okay.
Yeah.
So it's possible that the hafnium diboride oxidized when you did the measurements, and you're measuring some hafnium boride oxide. Whereas palladium doesn't oxidize really, right? So you still have palladium.
I mean,
Hafnium diboride is very resistant to oxidation.
Oh, it is there.
Really does not.
He just said it oxidized.
I've seen some
does not
oxygen peaks in the XPS.
It does
Yeah.
not.
Yeah.
Okay.
Yeah.
I mean, I don't think it would change the results because you have a resistive contact, is there a resistive contact? I'm just wondering if that Venn diagram is perhaps should be modified. I don't know.
Okay.
I'm always suspicious of, when somebody says the work function of this is this much, right?
Mm-hmm.
I'm always suspicious of those work functions when they're exposed to air, when they're really thin films, when they're, you know what I mean? Like, but I think if you're just trying to make the point in terms of qualitatively, it's probably right.
Okay.
Right. That's all. And I had one more follow-up question. Do you see evidence of the metal depositing preferentially onto semiconducting or metallic nanotubes? Can you tell?
I think, yeah, it's more depositing, well, in terms of junctions, junctions formed by metallic and semiconducting tubes will be more resistive because there is an additional Schottky barrier for those tubes. It really depends on the separation gap between the tube and the angle, the geometry of the junctions. But the metallic and semiconducting tubes, I think it's metal is more preferentially depositing there. And also on some of the tubes that we coated, I think those were the semiconducting tubes too.
I see. So when you show the crossbar at the end, the tube
Where
that was fully coated, you
Right.
think that was a semiconducting tube.
Well, that,
Can you go back to that part?
Yeah, I can.
It still showed an on-off ratio. So I'm thinking if you fully coat a semiconducting tube, it basically becomes a metallic nanowire. It shouldn't, it should be all metallic.
so this device was, I'm not sure either one of these two tubes were semiconducting because they were turning on and off. They still turn on and off after, but you had a high increase
Do you have
in.
the ID for this particular device?
Not here, but yeah, I do, yeah.
Okay. We'll talk about that offline.
Okay.
That's fine. Thank you.
Just a follow-up, maybe to Eric's question. Have you tried deposition with gating off your semiconducting tubes to see if you can isolate metallic junctions?
I have, yeah. It works better with the gating the devices. I have in the past where I was trying to fit the parameters to find the conditions to deposit with these metals, and I usually ended up putting the entire pathways. So that's that's possible, but I found that with gating works much better. So I've been working more with gating. Yeah.
Or that might be one way to identify.
Right. Okay.
Any other questions? I guess one final question. So if you showed the results for the crossbar structures, you didn't show the results for the palladium on the thin films, if I remember correctly.
Mm-hmm.
So could it be that you're getting an enhancement due to the fact that you're doing multiple transfers of carbon nanotube films, introducing residues between layer 1, layer 2, layer N, whatever N may be, and that the junctions are more resistant because it's carbon nanotube junk carbon nanotube rather than carbon nanotube carbon nanotube?
No, I do think that these crossbar devices, which has gone through more transfers and etching steps, are more defective. I did have film diver deposition on these devices too, but it did not show large improvements.
Okay.
Yeah. And palladium on network devices is ongoing work. Yeah.
Okay. Any final questions? If not, let's thank Jae Won-Do.